I just wanted to share with you, first of all, show you where I work. I work here, British Antarctic Survey. It's down the end of the road, round the corner behind the tree. And the reason I want to show you that is because every morning when I cycle to work, I cycle past Ada Lovelace Road. So I just thought that was a lovely thing and I wanted to just show you. So what I'm going to do tonight is tell you about two of my favourite facts. And really they're just two things which I think are really, really scientifically cool. Now, I'm an atmospheric chemist, so my favourite fact number one is about the atmosphere. And for this, I want just a little bit of help. So, can anybody tell me which is the most abundant molecule in the atmosphere? What gas makes up most of the atmosphere? Hey, fantastic. Okay, what a relief. Can anybody tell me how much nitrogen is in the atmosphere as a percentage? Very good. I'm doing it to 3 decimal places, if you don't mind. So nitrogen makes up 70.084% of the atmosphere. Okay, so what's the second most abundant gas in the atmosphere? Oxygen. Anybody know how much? Pardon? 21% is very good. 20.946%. So it's actually quite a lot, isn't it? When you add those two together, you've now accounted for 99.030% of the atmosphere. There's a little gap in the pie chart there. What we're going to fill that in with. What's the third most abundant gas? Argon. Brilliant. Wow, fantastic. Do you know how much argon? You can sort of do the maths. Okay. Argon is 0.934%. Very good. So if we add those together, we've accounted for 99.964% of the atmosphere. So we have a residual of 0.036%. What does that look like on my pie chart? Well, you can't really see it. Okay, so I say I'm an atmospheric chemist. What is there to study, you know? Job done? Well, of course, no. Because in that tiny, 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 tiny little bit of the atmosphere, we have loads and loads and loads of different gases. They're called trace gases because they're present at really, really tiny trace concentrations. This isn't all of them. This is just what I could fit on my slide. So, thousands of them. So, let's have a little look what's in there. We've got carbon dioxide. We've got methane, the greenhouse gases. We've got ozone, which is so important for shielding us from the sun's ultraviolet radiation. We've also got the CFCs, which destroy ozone. We've got nitrogen dioxide, we've got sulfur dioxide, we've got nitric oxide. These are all pollutant gases. So we've got, in that tiny, tiny, tiny little percentage, we've got all the things which we hear about. Ozone hole, ozone depletion, CFCs, acid rain. That is all going on in this 0.036% of the atmosphere. And I think that's pretty impressive. So let's just think about how much of these gases there are. Carbon dioxide, which we know is really, really important, is present at about 400 parts per million. Now, what this means is that for every million molecules in the atmosphere, 400 are carbon dioxide. So it's a bit hard to get your heads around. I find it hard to get my head around things like that. So if you think about it in terms of time, 400 parts in a million is the same as 400 seconds in 11.6 days, because there are a million seconds in 11.6 days. So it's not very much. Nitrogen dioxide is present in London. It's very variable, so I kind of stick my neck out. But again, you know, let's not get pedantic. We can say roughly 40 parts per billion. So for every billion molecules in the atmosphere, 40 of them are nitrogen dioxide in London. And that's equivalent to about 40 seconds in about 32 years. And that's actually quite polluted. So I work at the British Antarctic Survey. A lot of what I do is studying a really, really clean atmosphere. This is my laboratory. Oops, sorry, no, it's not. That's my next slide. This is my laboratory in Antarctica. And we study gases there at concentrations of parts per trillion, but we're not going to go there. So we do work to understand the kind of the clean background atmosphere and how it works. Another thing which we're interested in doing is to understand how a signal in an ice core is built up and how we can interpret what you can get by measuring ice cores. So this is my next slide. So that is a beautiful picture of Antarctica. It's a fairly typical picture of many places in Antarctica. And there are places in Antarctica where the ice is about 3.6 kilometers deep. So it's really, really deep. And the snow, which has fallen, is buried because the snow falls and then more snow falls and more snow falls and it doesn't melt, it just gets buried and buried and buried. And so the snow at the bottom of that layer of ice can be about 1 million years old. And when snow falls, snow's a little bit fluffy, we don't see so much of it here anymore, but it's a little bit fluffy, and so there's air around the snow. And so you bury the snow and you've got some air around it. You put more snow on top, there's sort of more air, a bit more, and you sort of squash it. And as you squash it, the air forms bubbles. And you can drill an ice core, which is what these people are doing here in Antarctica. In there is the ice. I hope you can all see that. There's about a 10 centimeter diameter tube of ice, solid. And that is the barrel of the ice core drill. So there's your ice core. And if you drill an ice core, you can section it and you can see beautiful things like this. So this is a cross-section of a piece of an ice core, and the structure in it, those are the bubbles. And you can hold your ice core, you can hold offcuts of an ice core. And if you warm them, you melt them in your hand, you can listen to the bubbles bursting, and you can sniff very, 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 very old air. But of course, that's not why you drill an ice core. You drill the ice core so you can analyze the air. And that brings me on to my next favorite fact. What I want to do is show you what ice cores can tell us about greenhouse gases and how they've changed through time. So we're going to look at the story of carbon dioxide. I'm going to use the pointer, and I hope that's okay for you all and that you can see it. It's just I quite like pointing at things. So what we've got here are measurements of carbon dioxide made in the air. Okay, so we're starting off with the air. Somebody has taken samples of air and they've analysed them to say how much carbon dioxide is in them. And they've been doing that at South Pole since 1957. It's actually the longest CO2 record in the air in the world. Mauna Loa, South Pole. Anyway, credit to the two institutes in the States which have been doing this work. And what you can see is that from 1957, we've got a time axis on the bottom, goes from about 1950 to about the present day. And on the side, we've got CO2 going from about 300 parts per million. We talked about parts per million, up to about 400. And what you can see, there's a wiggle. That's fine. That's natural. We call it the earth breathing. It's kind of the balance between respiration and photosynthesis. So you do get a variation as you go through a year. But you also see this very kind of noticeable increase in concentration. Okay, so these are the air samples. So what I'm doing here, these are still the air samples, but I'm plotting them differently. Okay, so they're plotted on different axes. It's the same data, but now the scale goes from 1,000 years ago to the present day, and I've also shifted the CO2 scale as well. And because scientists are kind of nosy, curious people, you think, well, you know, it's great. It's nice to see what's been going on since 1957, but what was happening before that? Is there any way that we can find out? And of course, the answer is yes, we can, because we can use ice core data. So the blue line here are measurements of carbon dioxide that have been made by drilling an ice core in a place called Lower Dome in the coast of Antarctica. There's South Pole in the kind of the middle, and extracting the bubbles and analysing the carbon dioxide in the bubbles. And that's fantastic. So we can see that over the last 1,000 years, pretty much carbon dioxide has been fairly flat in concentration, and then it's gone kind of boom. Right, so as I said, there is ice in Antarctica, which is about 1 million years old. And it's been drilled to 800,000 years. And the bubbles have been extracted and analysed for carbon dioxide. And now we get this pattern of carbon dioxide going back through time. I'm sticking with in red here. This is still the South Pole data in the air measurements since 1957. The blue is still the Law Dome ice core data. This is what we've looked at already, but now I've added into this the Dome C ice core drilled at Dome Concordia here. And what you can see, it's not flat, it varies. So there is structure, and that's interesting. Now this is natural structure. What you get signals in carbon dioxide according to glacial and interglacial periods. So the glacial period is when it's cold, and the interglacial is the period in between. And you get a cycling like this roughly every 100,000 years. So here we go, here we are today. That's the previous glacial period. That's the previous interglacial, glacial, interglacial, glacial, interglacial. And we can go back through time like that. What is really, really clear is that over the previous 800,000 years, we have never been outside this envelope. There's natural variability, that's fine, but the Earth maintains carbon dioxide levels within this natural envelope. But we're up here now. We are 30% higher than we have ever been in the previous 400,000 years. Does this matter? Well, here we have a plot of carbon dioxide. This is just the Dome C data now. Carbon dioxide, the data that I just showed you, going back in time between the present day, except it's not quite the present day, but you can't see the last bit on the plot, 800,000 years ago. And I've also plotted temperature. Temperature is plotted relative to today, so it's a temperature difference. And I'm going to leave it up to you. You know, you tell me, do they vary together? Do you get the temperature changing as the carbon dioxide changes? Well, I think that you do. What's going to happen next? That I can't answer. What I can do, though, I've brought some ice. Now, I'm not going to get it out now, but I have a suitcase down at the front, and I have some of these offcuts because the very lovely ice core people that I work with at BAS have given me some offcuts. So if anybody's interested, at the end of the evening, you can come down, you can hold some ice, you can melt it in your hand, you can listen. And the ice is about 1,000 years old, so you can smell what it was like at the Battle of Hastings. Okay? Thank you very much.